Which of these rocks is bigger, the one on the left or the one on the right? Are they about the same size, or is one twice the size of the other? Photographs can trick us because all photographs are two-dimensional representations of three-dimensional space, and they hide the distance. Without some sense of distance, without references, it is hard to tell how far away an object is. Let's move around to the side and look at the same rocks from a different perspective. Now it is obvious that from our original vantage point, they were different distances from us, and now it is a bit easier to tell which one is bigger and which one is smaller. When we place them at the same location, it is even easier to judge their relative sizes. So it is with the pictures that you're seeing from the JWST and the Hubble telescope. If we truly want to understand these objects, one of the questions we need to answer is how far away they are. Only then can we determine their actual size. So with that in mind, let's go through the pictures that you'll see hanging in the exhibit room and give a distance perspective to them. Before we start, let's say something about distances. Astronomers use light years to measure the distance and size of objects which are far away in space. The moon is far away. In fact, it is the farthest distance from Earth that astronauts have ever been. Yet it takes light only about 1 second to travel to the moon from Earth. So we say that the distance to the moon from Earth is 1 light second. The sun is about 8.5 light minutes away, and the farthest planet orbiting our sun is about 5 light hours away. When you compare spending 5 hours at work or school to every hour in an entire year, there are almost 9,000 of them, you begin to appreciate how long a distance a light year is. The nearest star to Earth is about 4 light years away. So beginning with the pictures of the formations closest to us, let's consider the star-forming region, Rho Ophiuchi, and the protostar found in L1527. Both are about 460 light years away. Let's represent that distance by a simple blue bar. Next, we come to the Horsehead Nebula and the Hairbig Haro object 4647. These are approximately 1,400 and 1,500 light years away. That is 3 times the distance of the earlier objects, so we'll represent them with a red bar that is 3 times the length. Moving on, we come to the famous and beautiful Planetary Ring Nebula. It is 2,600 light years away, 5 times further than the closest objects. You'll see that we make a big jump in distance when we move to the Pillars of Creation and the Crab Nebula. They are both about 6,500 light years away in different directions of the sky. Next, we come to the Cosmic Cliffs. This picture is one small part of the huge Carina Nebula. The distance of that nebula is 8,500 light years away. In our local neighborhood, the farthest object on display is Cassiopeia A, the supernova remnant of an exploded star. It would take light 11,000 years to travel to Cassiopeia A. That is an incredibly long time. However, the fastest satellite ever launched from Earth would need much longer, 18 million years, to travel that far. That shows how fast light is and how big our galaxy is. Even though it's hard to imagine these distances, they are still small compared to the size of our entire galaxy. The next object, Sagittarius C, is thought to be near the center of our Milky Way galaxy. That distance is 26,000 light years away, and it's too big to show with our current scale, so let's pinch in a bit. This is the distance from our location to the center of our galaxy. So how big is the entire Milky Way galaxy, and how much space lies beyond it? Here's a photograph of the galaxy that we see from inside. The length of this picture represents the diameter of the galaxy. Astronomers estimate this to be over 100,000 light years. The distance from our sun to the center of the galaxy is about 1/4 of the diameter of the entire galaxy. Of course, we have never been outside our galaxy, but here's an image of what the galaxy might look like if we could see it all from the outside. Each yellow circle is centered on the sun, and represents a different distance away. The objects that we have placed so far are represented by these small markers near the sun. You can see that the center of the galaxy, the bright bulge directly above the sun, is much farther than the objects we have seen so far. One of the remarkable things about the Hubble and JWST telescopes are that they not only capture light from beyond our galaxy, but that they do so with a resolution that allows us to see size and structure to these distant objects. Look again at the picture of the Milky Way galaxy. This small object below and to the right looks close, doesn't it? But remember that photographs hide depth and distance. That blob is actually the Large Magellanic Cloud. It's a separate galaxy well outside the Milky Way with a diameter of more than 30,000 light years. The Tarantula Nebula, shown in the exhibit, sits inside of the Large Magellanic Cloud at a distance of 160,000 light years. This shows the relative distance and size of the Milky Way galaxy and the Tarantula Nebula. The tarantula is also the largest object that we have looked at. At over 900 light years wide, this nebula would stretch from Earth close to the distance of the Horsehead Nebula. And yet, because of its great distance, it appears as small as a grain of salt held 6 inches in front of you. Our large space telescopes are able to reveal structure in this nebula like a microscope would see in a biological cell. As we go even further, it is more difficult to precisely determine the distance to extreme galaxies. The measuring rods we use as distance markers are harder to find and they blur together. The face-on spiral galaxy, NGC 1566, is at least 100 times farther than the Tarantula Nebula. The best we can say is that it is somewhere between 20 and 70 million light years away. And still these telescopes show clear structure within an object which appears as big as a grain of salt held 8 inches away. Finally, we come to one of the primary limits which JWST was designed to reach. The Webb telescope collects over 5 times the amount of light which the Hubble telescope does. This allows us to see structure in even more distant objects. Each dot in the Webb deep field image is a galaxy with perhaps billions of stars in each one. Astronomers have counted at least 7,000 individual galaxies in this image. We can see the apparent size of the galaxies, but structures such as spiral arms or nebulas are too small to be seen. The distance to these galaxies is determined by comparing the size of the dominant wavelengths of the light that they emit to the wavelengths of known gases, such as hydrogen. This is what astronomers call the redshift. The closest galaxies in this deep field image have been determined to be about 4 billion light years away, and the farthest may well be over 13 billion light years away. For the first time, our telescopes have allowed us to identify galaxies at this distance. And remember, looking far out into space is looking far back into time. As we study the size and structure of these objects, more discoveries will be made, and our understanding of the universe that we live in will be clearer and deeper.